All right, so in this final week of the semester, we are going to um, talk about analysis of biological networks, and we are going to see two problems: uh, clustering and random walks on graphs to find proximity of nodes to a group of other nodes. And this is to clustering is to find densely connected subnetworks in this largely sparse network. So we have seen last time that even the 8.5 million edge network of the string is a sparse network because there are possible of 200 million uh, edges between those 20,000 nodes. All right, so that's the we are going to see analysis methods to do that. And before we start on the clustering method, I want to make sure you understand how we're going to be representing graphs. And you will be using something similar for your last assignment. Last assignment is going to be a programming assignment on biological networks. It's not going to be a difficult assignment. You may even use the code that I give here as a starting point. It will be just to measure certain graph-centric properties about the nodes, okay? And it will be due, let's talk about that as well. It will be due up at the end of the final exams, around July 12th or 13th, so a couple of days after the final exam. So you will have about 3 weeks to work on the assignment. Depending on your schedule, you may it will not take more than a day. Okay, so as I said, it will be an easy graph analysis programming assignment, but I will give you 3 weeks to work on anytime you want according to your schedule. It will be as July 13th, Tuesday or something. It's going to be, I think July 11th is Sunday. So it will be due July 13th, Tuesday. To also, we need time to grade the about 80 assignments. So therefore, we cannot delay it more than that. But you will have plenty of time to work on it. So that's about the assignment that you will be doing, your last assignment. And also the final exam, you're going to have it next week on Tuesday at 1:30 p.m. Its conduct is going to be very similar to the midterm exam, and it will include topics after the midterm exam. I'm going to send an email about the final exam today or tomorrow, latest. But as I said, the main thing here is that it will be similar. You will not need to open your camera, turn on your cameras. The exam is going to be online on OttiClass in a fixed 2-hour interval. You will not get a fixed time, but the exam will be open at a fixed time at 1:30 sharp, and it will close at 3:30 sharp. So if you log in late, you may lose a couple of minutes. It will end at 3:30. And it will be the exam questions, as I said, the types, so there will be some numerical questions, and it will be like an open book exam that you had in the midterm exam. If you have any questions about the final exam, I'll be happy to answer. There will be some small short answer textual questions that I will grade manually, and there will be also some numerical questions that you will have to compute and enter your numerical answer. But it will be just very similar, parallel to the midterm exam. The only difference will be the topics will be covering which I will send you today or tomorrow. It will include the topics after the midterm exam. It's not a whole comprehensive final exam. It's just like a second midterm exam. You may think about it like that. Right? So today, my plan is to finish at least clustering and start random walks. And the methods that we are going to talk about on graphs today will work. I mean, these algorithms are going to be working on graphs in which we have to have some kind of a representation in memory. And this is the hash table of hash tables, which is an adjacency list representation of graphs. If you're going to read for this on some books, algorithm books. The graph representation that we are using is called adjacency list. Adjacency list representation. And the adjacency list representation of a graph is suitable for sparse graphs especially. And the way it works is that if you remember the adjacency matrix representation of a graph, it's an n by n matrix where the entry ij here, if for example this is the ith row and this is the jth column, okay, the ijth entry shows the relationship between node I and node j. If it's 1, for example, it may indicate the existence of an undirected edge. If it's 0, it may say that there is no edge between I and j. When I say undirected, actually, the way the matrix is represented, there is direction because we have rows and we have columns. So a row ij may indicate an edge from I to j. Okay, so the semantic representation of a cell here being 1 is there's an edge from I to j. Now, if we have an undirected graph, obviously there will be the other entry ji in the symmetric matrix. If this is a diagonal like this, ji will be somewhere here. So I actually not here, but somewhere here. I mean, if you want to make it look like symmetric. So this will be the jth entry, and there will be two, for an undirected edge, there will be 2 entries in the matrix that are 1, both for ij and ji. Okay, so therefore this matrix is going to be symmetric for undirected networks where we will have edges ij and ji both be represented in 2 cells. If we have this adjacency matrix representation without changing anything is suitable for representing directed networks as well. All you need to do is if you have a directed network in which the edge is given only from I to j, you shouldn't enter the second cell to be 1. It could be 0 if the other direction edge doesn't exist. We will just have the direction edge from I to j 1 and j to I may be 0. In this case, the matrix is not going to be symmetric, and we will have non-symmetric directed network like this. And we can use this adjacency matrix representation to represent both directed and undirected edges on the same graph, like the pathway commons network. If you remember the pathway commons network, let me open that again. That was this one. It contains edges which are undirected in nature, like this one. A protein being in a complex with another protein is an undirected edge. But if you look at this one, a protein controlling the state change of another protein is a directed edge. So you can represent all these things, and you can even, instead of having just ones and zeros, here, the entries of this matrix can be anything. It could be, for example, 0, 1, 2, 3, 4 different integers, which you may use them to code, for example, oh, if it's a 2, it means this control state change of. Oh, if it's a 1, it means they're in complex. So you can actually label your edges by putting different values in your adjacency matrix. It doesn't need to be necessarily an integer matrix. It could be floating point to indicate floating point weights, or it could be a matrix of characters, single characters, if you don't want to code them with this like this, or it may be an adjacency matrix that contains strings in these cells, where you can directly write controls expression of as an edge label into this cell. But in this adjacency matrix, if we have a matrix like this, m by m matrix, the bad thing is that a lot of the entries of this matrix is going to be 0 anyway, because it's a sparse matrix. If n is equal to 10,000 or 20,000, okay, if n is equal to 20,000, what we will have is we will have a 20,000 by 20,000, a matrix with 400 million entries. Okay, if you multiply these to 400 million entities. For an undirected network, you may want to use only the half of this network, which will give you 200 million undirected edges. But still, if even the string network, which is quite dense compared to other networks, there were 8.5 million edges in that, which means that it's going to be its density is going to be 8.5 divided by 200 million, which is going to be like 4%. It will be around 4.2 4% full. 96% of this matrix is going to be all filled with zeros. Okay, these zeros, if you don't give them any values, if you have yourself an integer n by n matrix, if these are integers, okay, if these zeros and ones or two threes, you use an int integer which occupies 4 bytes in memory in many systems, which it means that you're going to be needing about 1.6 gigabytes of memory just to put this matrix, and you will be wasting about 96% of this 1.6 gigabytes for just all these zeros. Even though they are zeros, they will, if you get yourself a matrix like this, it's going to occupy space in memory. And therefore, the adjacency representation avoids this. Instead of having the entire matrix as an n by n matrix, why don't we have this? Now, instead of the matrix itself, why don't we, for each row, okay, 1, 2, sorry, 1, 2, 3, if these are the row numbers, and this is n, instead of having the entire row for gene number 1, okay, which will be, if it's a matrix, it's like every row is exactly an array of length n if it was an n by m matrix, right? Now, the idea of the adjacency list representation is that many of these entries are going to be zero anyway. Why, instead of having the entire row, why don't we list the neighbors of 1? Okay, for example, 1 is neighbor to node number 3, it's the neighbor to node number 8, it's neighbor to node number 100, 1011. If we just list the neighbors and we don't need if it's a list of neighbors, then the zeros are not stored here. So what will happen is that the size of this adjacency list will be n times the average degree. If d is the average degree, average number of neighbors of a node, so actually the number of things that we stored here is exactly 2 times the number of edges. Each edge is stored here. For example, the edge between 1 and 8 is also stored. It means that 1 is listed in the list of neighbors for node 8. Okay, so this is node 8. Since if there's an undirected edge between 1 and 8, there should be the same edge between 1 and 8 should also be represented here in the adjacency list of node 8. Therefore, if I have this many edges, there were like 1.6 million edges in the pathway commons network, right? Let's check that again. If I go to the end of this list, oh, it's actually 1.3 million. There are 1.3 million edges in the pathway commons network. If, assuming in the worst case they're all undirected, directed edges will just count for 1, but if we all the edges we have are undirected, this entry is going to be, we will have to store 2.6 million integers in this adjacency list representation. Again, if you're just using integers for your node IDs, it will be 4 times this one, which is going to be 10 megabytes. Okay, compare a 1.6 gigabyte memory requirement to a 10 megabytes memory requirement. Okay, so this makes your program much more scalable to larger networks, this adjacency list representation. This is basically, instead of having the entire matrix, using the adjacency list representation makes it possible to store very large networks. If they are sparse, adjacency list representation will be very efficient. One drawback of adjacency list representation like this is when you're looking for, when you ask questions like, for example, is node number 800 or 700, is this a neighbor of node 1? If we ask a question like this, we have to go through in the adjacency matrix representation, the existence of this edge could be found in O1 time, in constant time, by just looking at the adjacency matrix entry 1700. Okay, so you would immediately go where 700 is located. You will immediately go to that cell to figure out whether 700 is a neighbor of node 1. Now, in this adjacency list representation, we no longer have the indices, it's just a list. In order to look for existence of an edge to 700, what do we need to do? We need to go through this list one by one and look for 700. If it's there, then there's an edge. If it's not, then there is no edge. But we have to go through the list. So instead of O1 time, the average running time of such query will be OD time, where D is the average degree. So which means that we have to go through all the neighbors one by one to do this. So a better approach than to have, I mean, you could have listed these list of neighbors. You could have put them into a vector, which will allow you only to go through them one by one. But now, a better representation that I have shown you in my implementation, which I told you hash maps or hash tables or maps, allow you to do such kind of queries also in expected O1 time. And it's another added advantage of using hash tables for this adjacency list. Instead of having an adjacency list, why don't I have an adjacency hash table? Which will, if I will ask, for example, is there a key that with 700, existence of a key in a hash table could be found in expected O1 time, and I would be making these queries, just saying, is key 700, does the key 700 exist in the hash table? Is the same as, similar to asking this, whether this cell is 1 or not. Okay, now, and the added advantage of using hash tables is that you don't need to encode your nodes with integer IDs. If you have a matrix, the matrix indices are usually given as integers, okay? But in Python, we have dictionaries. Basically, the Python dictionary is the same as a hash table, okay? It's a hash table, basically, or a map. A map is something that maps key with key value pairs, okay? And these keys are like indices that you use. And the good thing is that these keys in regular arrays are keys, are these integer indices. But in dictionaries or hash tables or maps, these keys could be of any type. So instead of having 1, 2, 3 encoded node names, you can use your gene names like AC2, TOP1, top1, AC2 gene. You can have, instead of having these numbers, you can have your gene names as your key values, and you would be asking things like, is AC2 a neighbor of top1? And we will be accessing those things. So what happens is that this the list of rows here, for example, where is top1, or where is, for example, CDC6? There's this gene, for example, CDC6, at which row it is. If you were to represent this as an array which was indexed by integers, you would have to look where CDC6 is. You would have to look for it one by one, which would make it very inefficient. But if you use a hash table for the names of these, for the row IDs, so this is the hash table, okay, itself, the rows, the list of rows here, and each row, the data that is contained, in other words, for example, my main adjacency list is a hash table in which the keys are strings and the values are these lists, okay? In terms of a value, as a value, I will maintain the list. And the list itself is going to be another hash table, okay? So this main thing is a hash table in which that's my adjacency list or adjacency matrix. My A is a hash table itself. in which I will have keys. Each of these keys are like this. I will insert for every gene, I will insert these keys into my main hash table. And the values that I stored for each key is a list of its neighbors. And its list of neighbors, I maintain this list as a hash table, which is the key value pairs in this hash table, maybe a string here for the neighbor's name, 38, and it may be an integer. If I want to store ones or zeros, it may be a float, or it may be a string itself too, to indicate the label of an edge. It may say, for example, this value here may be say that it's in complex of, or it's control state change of, or it may be just, if you're just having an undirected, unweighted graph, the value here may just be 1 or 0, an integer. Okay, so you're free to represent how the relationship between this key and this key, basically this key becomes your one of the gene IDs, and inside its hash table we have a list of neighbors, and the neighbors are identified by their names as strings as well, and this value becomes the edge itself, and how you label that edge with one or, I mean, we don't need to have zeros here. For example, the absence of an edge, you don't need to add a gene here into this adjacency list, because that defies the purpose of having an adjacency list, right? I mean, if you're just going to put all the not absent edges also here into this adjacency list, it becomes an original adjacency matrix. So therefore, sometimes you may use, instead of these value, you may ignore that value. If the key exists there, it means that there's an edge between these two things, okay? You don't need to put one there. But if you have weighted graph, you're free to do whatever you want. And this is exactly what the implementation that you see here does. Okay, the first here, this A matrix, the adjacency matrix hash table that I initialized in Java, I initialize with 40,000 nodes. So it's in the initial value, it may contain hash tables. Usually it's good that they are like 50% or 75% full, in order to avoid clashes, collisions of these hashes. You need to have like at least 1.5 times larger than the intended number of nodes you insert. So it's okay to have a 40,000 size hash table initially. That's your hash table of rows. And then what we do is, when we read our edge list line by line, so this is the main loop. What you see here is the main loop that reads our edge list one by one, gets two string IDs. For example, I could have gotten, let's get back to the pathway commons network, which was tab separated, and second here I can call this edge label, okay, which was the first item. So when I split this, it gives me three things. So if you look at this pathway commons, there are three tokens which are tab separated on a single line. When you split them into three tokens, three strings, this becomes the string index at 0, 1, 2. Now, the 0, 1 is the ID of your first protein. This one is the edge label, which tells you whether it's control state change of, or whether it's in complex. And this is your second protein. Now I will do something interesting. I will just put both, for example, in this pathway commons network, I may say that I'm only interested in edges which are in complex width and control state change of. Okay, I will just ignore all others, for example, controls transport of, or if there are other edges. I'm just interested in molecular complexes, which are stable interactions. And I'm also interested in physical protein interactions which are transient, like phosphorylation, and which will be represented by this control state change of type of thing. So what I'm going to do is this in complex width. So let's see what I will do here. Oops. So I got my edge label. Depending on what the edge label is, for example, I can say if edge label equals in complex width, okay? If it's in complex width, I will add an undirected edge to my hash table, okay? And adding an undirected edge, what does it mean to add an undirected edge? It means that adding this edge to the adjacency list of P1 and to the adjacency list of P2. And the first part, let me just quickly tell you what this code is, and this is where I'm going to close this off, okay? So if the edge label equals in complex width, this highlighted if-else loop adds the protein P2 to the adjacency list of P1. First, in order to do that, we look at in our matrix, did we have, does the P1 exist in my row list? This is asking that, have you processed a previous neighbor of P1 before? If it was, if P1 already exists in the adjacency matrix with this query, which I'm asking that, it will tell me that, oh, okay, P1 had some previous neighbors already inserted. So what I need to do is, if it exists, okay, I need to get this neighbor list. So, okay, so give me its neighbor list. And after I get its neighbor list as a hash table, I add a new neighbor to the adjacency list of P1. And I just use this as values. I use this floating point weights, so it's like a weighted graph, but they're all 1.0. So I'm in my code, actually, I'm going to ignore all these, okay? So I will just look at, I mean, you can, as value here, you can insert anything. You can insert some, if it was a weighted, confidence weighted network, you can put your confidences here. All right, now, or I can say, for example, I can insert an edge. If I want to distinguish between these two edge types later, controls in complex width and control state change of, I can actually add an integer here to indicate, for example, 1 means in complex width, 2 means, so I don't need these columns here, 1 means in complex width, 2 means controls state change of, okay? So therefore, right now I'm inserting an incomplex width edge, therefore I'm adding an integer 1 as its value pair. Now, the else part of this if shows me that if this is the first time you encounter the gene ID P1, it means that it doesn't have, and it doesn't exist in my row list yet. It doesn't have any neighbors processed before. So what I need to do is I need to create for it a new neighbor list. So this is this very smaller, much more smaller hash table than the 40,000 one, as you can see. This 20 is just some number arbitrary that I have chosen. I thought probably the average number of neighbors, I thought it would be like 20. You can make it 200. I don't know. I mean, it doesn't matter, this initialization. If the number of neighbors that you want to insert into this hash table is larger than 200, the hash table is automatically increases its size. Okay, so this is just for initialization. You may even initialize it with just one neighbor, but in that case, you will have to do this updating of its size every time you're inserting a neighbor, which will make your program a little bit slower. So just initializing with some intelligent guess of the largest number of neighbors you can have, or the average number of neighbors you will have in your node makes sense. So what I do is I create a new neighbor list because this is the first time I encounter P1, and I add P2 into its neighbor list. Right now, as you can see, this was a completely new adjacency list. I add P2 to that, and again I'm adding integer 1 as I did here, and then I add this P1 to my overall list of rows into my adjacency matrix. So this one adds P2 as a neighbor of P1, and I say the type of the edge is incomplex width. Now, since incomplex width is an undirected edge semantically, I need to do the exact same thing that I did for P1 for P2 as well. So this second part here is adding P1 this time as a neighbor of P2 because it was an undirected edge. Okay, so I repeat the exact same thing I did here for P2. First, I asked maybe P2 may have been processed earlier. P2 may be interacting with other things. So if this is false, for example, it doesn't mean that this is going to be false too. P2 may have been encountered earlier than P1. So we should ask again whether P2 exists in my adjacency matrix or not. If it exists, I get its neighbor list and I add P1 to its neighbor list. Look at my keys. My keys are strings here. P1 was a string. Else, if P2 also did not exist, I also create, let's also make this 200 to be consistent. But as I said, it's not that critical. So I also add an integer. So this code that you see here inserts an incomplex width edge between P1 and P2 that we encountered in this graph traversal. Now, I'm also interested in the control state change of edges. So let me also do that. What is this control state change of? If P1, which was edge label, sorry, not P1. If edge label equals control state change of, okay? Now, what I will do is, let me put it here. I will just copy this one here and only this one, not the other way around, because this time control state change of is a directed edge. Okay, P1 controlling state change of does not mean that P2 controls state change of P1. Okay, so it's since it's a directed edge, I will only add P2 to the list of P1, and that's it. So control state change of actually, the code for control state change of is going to be shorter, and this time I'm going to add integer 2 here. Okay, now here's a thing that you may need to consider. What if both types of interactions exist between a pair of genes? What if they are both incomplex and one of them controls the state, controls the expression state change of the other? This time, this implementation that we have chosen is not going to be suitable for that, because we just overwrite whatever value we had before. We would be overwriting the previous value. In that case, if our edges are able to have multiple labels on them, then we need, instead of just putting single integers into these edge labels, they need to be also vectors. Okay, I will ask, for example, when I'm inserting this, I would also need to ask, for example, if this n, so I will have to write some code like this: if n contains key P2. Okay, so when can this happen? If P1's neighbor list already contains P2. How can this happen? It means that there was some other edge between P1 and P2 that I processed before. And it was probably, for example, an incomplex with edge. In that case, instead of having just replacing it, I would accumulate all those different edge labels together into a vector, or I may concatenate them into a single string, whatever you chose to do. But I'm just going to ignore that part. For this simple implementation. It means that whatever edge comes later, it's going to overwrite the previous information. All right, so yeah, with this, I mean, let's see if I just look at these type of edges, what I have. So is this part of the code clear? Now uh, I, I have, after I finish this while loop, I have myself in memory an adjacency list representation that is exactly like this. I have a hash table of rows of protein names, which I can access with their string IDs. I can access their neighbor list. I can, for example, query the size of the neighbor list of each of them. I can insert new neighbors, delete neighbors from these dynamically. So the neighbor list basically is a hash table as well. So if I run this code, let's run it. Okay, it compiled with no errors. So Java read network, it was pathway commons network. So when I run it, now it has I think it was 30,000 in the original network where we considered all types of edges. Uh, Probably many of them were just chemical compounds because the pathway commons network also contained chemical compounds. If we just focus on, I mean, there are here about 10,000 nodes in the network, all of which are proteins, genes. Actually, they are proteins because it controls state change of. It probably is about phosphorylation type of interactions, transient interactions, but it's between two proteins. And when it says it in complex with, it's also between two proteins that form a larger protein complex. So there are 10,000 nodes in our network. And we can also ask, for example, we can compute how many edges there in our network. We can, for example, go over the entire network to look for how many incomplex with edges are there, how many directed edges we have. We can compute the average degree. For example, I will write a simple code here to compute the average degree. Okay, uh, so enumeration. So to go over, you need an iterator or kind of an, so I will get the A matrix keys and has more elements. So the functions that are available to these hash tables differs from language to language, but they will have to have these basic functions. You need to have some kind of an enumeration function to go over all of the keys that are stored in your hash table. You need to have queries that says get the value of this key, or also you should also have the query to ask for the existence of a key in that hash table. So right now, so let's get, for example, string p1 is going to be a string. And by the way, I'm not using the template idea, so that's why this is an old-fashioned way of typing this code actually. In the modern way, since the hash table keys can be anything, you should use the template, you should indicate its type while you're declaring it. The value of the keys could be declared when you're declaring your hash value, but this is the old way of doing that, but it will still work. So you need to cast that generic object, this and next element is going to give you. So this is going to give you an object, and p1 becomes your string. So what I will do is hash table get its neighbor list, hash table its neighbors, let's call it neighbors, neighbors is equal to p1 dot get, not p1, a matrix dot get p1, so I get its neighbor list. And I will do this, sorry, a matrix, I will do this for all of the keys. So this for loop goes over all the proteins in my A matrix one by one. Okay, I will process all of the proteins one by one. So I will get as neighbors, neighbor list of all of them. All right. Now, all I need to do is I will accumulate something. Okay, like total num edges. Let's have this one, which is I will initialize it to 0 here. And total number of edges is equal to total number of edges plus neighbors dot size. Okay, so neighbors dot size tells you how many neighbors P1 has. So this is the degree of every out degree actually, but since we have directed and undirected edges together, so it will sum accumulate this neighbor list, size of the neighbor list of every node in my network. And at the end here, for example, I can print total number of edges is equal to this total num edges. And I can say system out.println. So, and I can also say the average degree of the network is, what is that? It is total number of edges divided by a matrix dot size. Okay, and I can have one of these this is going to be an integer division. So if you want this to be a floating point division, you just cast one of these to a floating point, the total number of edges, for example. Oh, by the way, I need to have this not right here. Actually, this enumeration also should be underneath here. I don't want to enumerate after, I don't want to do this every time after I read a single edge. After the entire graph edge list reading is completed, I do this for loop after I read the entire graph. I go over all of the edge list one by one. I get how many edges you have for each gene. I accumulate that. Also, I need to put it outside. I forgot to put it outside as well. All right, so this is, let me work on, so the total number of edges is this, and the average degree. So let's run this code, and then I'm going to go back to our slides to talk about the methods that we can implement on this graph representation. Yeah, so I'm missing one parenthesis here. I think it was going to be here. Yeah. So why do I flow? No. It should be here, I think. Oh, no, no, no. It's correct. Yeah, it compiled. Let me run it on our network again. So where was it? Yeah, this one. So when I run it, so as you can see, it finished in an instant. It was a large network with 1.3 million edges. But this hash table of hash tables representation, I have a couple of students which didn't know how to this adjacency list representation using edge list. They implemented their graph by using vectors, and it took like an hour or a couple of hours to read this network and do any analysis. Even reading the network in memory is going to take a lot of time if you just represent your list of rows as a vector and looking for every time you're adding an edge, you're looking in order to find this corresponding row of that edge. If you spend O(n) time, it will take a lot of time. With the hash tables, all of these operations, locating the row, getting its neighbor list, and all these things take O(1) time on the average, so it becomes super efficient. So the a total number of edges, about those 1.3 million edges we had in the network. But yeah, it's not actually 1.3 million. If they were all undirected, it will be like around 2.6 million. But about 1/5 of those are by the way, this number here is the total number of both. This is like representing each undirected edge as two edges, because when we were doing the accumulation, doing the counting, we counted an undirected edge twice, both in the neighbor list of P1 and P2 when we came to that. So here this count contains the undirected edges as twice. And also if there are two edges, both directed and undirected, between a pair of nodes, one of them is ignored because we didn't have multi-edge labels. We just use single edges. But roughly the number is around like this. And the average degree of the network is 51. So each node gene in the network, each protein in the network has 51 neighbors on the average. We can also do things like this quickly, and then I'm going to have a break. For example, what is the minimum? I mean, which gene is the loneliest gene, and which gene is the most popular gene with many edges? So we can also do that. And min degree, let's call it min degree, max degree, and also let's maintain their IDs too. String min d max d. So min degree, I'm going to initialize it to a very large number, like 90,000. It cannot be 90,000. I have 10,000 nodes in the network. And max degree, I'm going to initialize it to a very small number, like 0. And here's what I'm going to do. After I get neighbor size, if its neighbors.size is greater than max degree, what I'm going to do is max degree is equal to neighbors.size, and max d is equal to p1. And I will do the same thing for the minimum degree. So I'm keeping track of here, I'm trying to find the genes, the proteins, which with smallest number of connections. Oh, by the way, this is should be max degree. Max d is the string, and min d is this, the name, min degree. All right. If then min degree is going to be this, and min d is going to be p1. So with these two if conditions, I'm also keeping track of the maximum and minimum. And let's report that after all of them are processed. Let's report these two. System out println protein with minimum degree is equal to this min d, and it, so what am I missing here? Yeah, nothing missing. And it has min degree edges. Okay, let's do the same thing for the max degree. Protein with maximum degree, the most popular one is this, and it has this many edges. So let's also quickly take a look at this. And I will, after today, I'm going to share this code with you on OptiClass. So let's compile it. Oh, it may not, oh, okay. I need to also initialize these. So Java complains about initializations. So since this was in an if condition, the initialization of string names, they could be null potentially. I made sure they're not null by giving it appropriate values, but Yeah, Java does not know about that, and it complains about uninitialized variables. Okay, now it worked. If we run this, okay, so this MBPF3 has only one neighbor in the network, and there is this OGA gene. I don't know what this. It has 1,655 neighbors. So the degree distribution is highly asymmetric. I mean, although the average number was 51, there are genes with very popular, with many high number of edges, and there are also genes with very few number of edges in the network. So the next, after the break, we are going to talk about how this, uh, what what does this mean, and how we can make use of, for example, these values to do clustering to find highly densely populated regions in the network. Okay, so uh, I will first start with clustering of these biological networks and continue with random walks next. All right, let's have a 10-minute break now. If you have any questions, I'll be happy to answer them. Uh, but yeah, I will stop sharing my screen and first stop recording.